All right. So I think we've got a fair background at this point, kind of looking at metals and um, uh, how they behave in molecular orbitals and all this kind of stuff. So I wanted to transition into talking about some specific proteins now. And we're going to start with our buddy hemoglobin. I guess maybe because it's a good example that talks about a lot of the different features that we should think about and look at and kind of assess as we look at a different set of, or at the different sets of proteins that we're going to go through this semester. So let's start with the basics, right? Let's start with the basics. I'm going to be tabbing around to a bunch of different things here. Um, and so, real quick, I'm not going to take credit for stuff I didn't do, right? I'm looking at this website here, the RSCB, right? It's the Protein Data Bank. And this is a really cool website. It's a depository of all the different protein crystal structures that have been published and solved. And you're free to access this. It's free resource for everybody. You can download the different crystal structures and look at them and and they're just some beautiful structures. And I might maybe just spend a lecture kind of going through some of the cool stuff that I found in here. But we'll see. I don't know. Like, what should I title that lecture? Cool stuff that Dr. H wants to look at. Like, I don't know. I don't know what the value is in that, but it doesn't really matter. Okay, who cares? All right. But this is a crystal structure, right? If we're looking, hopefully you guys can see my mouse up here, right? We're looking at deoxyhuman hemoglobin. That means it's hemoglobin extracted from a human source, and that it's the deoxygenated version. I couldn't find a crystal structure of the oxygenated version. That's not too surprising, but maybe there is, and maybe if I do a little bit more digging, I'll end up finding one. But that doesn't really matter. Okay, so let's take a look at this real quick. So this is the crystal structure that you guys see here in the middle, and as I kind of start to move things around, right? Hopefully you guys start to, maybe see some stuff that you guys learned in biochemistry there. You see those kind of ribbons, and you see some twists, and some other different features of the actual protein itself. And I don't really care about those. That's not really something that I'm interested in for this course. A couple of things here that I wanted to just kind of point out to you guys is that hemoglobin is a tetramer. There are 4 units that are kind of globbed together here, and if you guys go to this website, and you guys can pause it here, and if you go to the website and search for 1A3N, right, you can bring this up, or just deoxyhemoglobin, you guys can probably find it that way too, right? So you guys can kind of, follow along with me if you want to. But there are 4 globs here that are together, okay? And these are going to be held together by the salt bridges. I think some of you guys talked about this, that you guys had already learned this in some of your biochemistry courses. And I'm not really going to talk too much about the cooperativity and all that kind of stuff, because I'm not saying it's not important, it's not relevant, and that's not what I mean at all. It's just, remember, the purpose of this class is I'm going to give you guys a tool set to interpret how metals work within protein systems, okay? And so just a different goal here. All right, but what is important? Okay, so let's zoom in on one of these different portions here, right? Oop, where'd it go? There it is. Okay. So right there, we see our good old buddy, the heme unit. Actually, you guys see 2 of them, right? So remember the heme unit. Let me see if I can get a good view here. Right, the orange part in the middle there is where the iron is, and the blue atoms that are around the outside are the nitrogens of the heme unit. And it's basically sitting in a porphyrin, right? It's got some other things kind of dangling off the other ends of it, but that's not too important for what we care about, right? But we've got an iron sitting within that porphyrin system, right? And that's what we call a heme. Something interesting to look at. I'm trying to give you guys the best perspective I can here. So, 2 things. The porphyrin ring is planar, okay? So the porphyrin ring, that seems like a pretty good view. The porphyrin ring is planar, but you can see, and it's subtle, right? But you see how the iron is sitting kind of outside of the plane of that hemoglobin, the heme center there. That's important. You'll also see there's a slight twist and bend, very subtle again, right? A slight kind of bend to the porphyrin ring itself. But a couple of important things to note. The iron is sitting outside of the plane of the porphyrin ring, and the porphyrin ring is kind of buckled, okay? And there are 4 of these porphyrin rings. You can actually see them in this view that we have here, kind of 2 in the background and 1 to the top left and the one that we're looking at here. So there are 4 of these porphyrin centers per hemoglobin molecule, okay? All right, if I go over here, okay. So I just did a Google search for, kind of a structure discussing or I looked for kind of the active site of hemoglobin here. There's a couple important things. So I'm looking over on the right-hand side here, where you see that kind of yellow and gray overlaid structure there. So a couple of important things, and we'll kind of break this down as we go through. But we'll notice that, there's the porphyrin ring. You guys can kind of see the porphyrin ring. There's the iron that's in the middle. Right? This has an image of the oxygen bound to it, and we'll talk about a little bit more about that in probably the next video, right? A couple of things. So on the other side of the porphyrin, there is this on the other side of the iron, there is this histidine ring. And this histidine ring is attached to the overall protein structure. And that's going to be important. Also, on the other end, there's this kind of dangling histidine ring here. And that's going to be another important feature, right? This dangling histidine ring. So when I talk about the active site of hemoglobin, let's take these ideas and transfer over here, right? There's my good old buddy, a heme unit, okay? My porphyrin ring, right? If you'll allow me to make some simplifications, right? So oftentimes you'll see the heme unit just kind of depicted, the porphyrin unit depicted like this, where it's the nitrogens that are just kind of bound together, right? We have an iron that's sitting in the middle, and this iron is bound to the 4 nitrogens in a planar system. Okay? And if you'll allow me to kind of twist this on its end, so what I'm doing is I'm basically rotating 90 degrees. So I have a nitrogen, right? Nitrogen. And so let's just make this a different color here. We'll do it red because we're talking about hemoglobin after all, right? So if you imagine, right, there's kind of another nitrogen sitting up in the front and in the back. So I'm just kind of looking at this from the side on, right? I'm just kind of looking at this. So basically I took this and just rotated it from the side. So if you imagine, right, this is the plane right here of the porphyrin ring. Okay? I hope that makes sense, right? I'm basically just taking all the pictures that we had and just kind of rotating them from the side. Essentially, whoops, that's the wrong tab. Essentially just doing what I'm doing here, right? Just looking at this directly from the side on here, right? And so if we do that, then down on one end here, we've got a histidine residue, right? Wow. This is getting kind of, I'm just going to write this like this. All right, a histidine residue, which is just coming from our good old buddy imidazole, right? And that's just bound to the rest of the ring itself. Whoops, I put that double bond in the wrong place. Excuse me. And then up at the top here, we would have another imidazole ring kind of just dangling off. Okay? And so if we kind of take this and try and depict it in a manner that's cartoonish to give us an example, okay, each monomer of the hemoglobin kind of has this kind of shape in it, where the porphyrin ring is kind of sitting towards this end, right? There's the iron sitting here, and the imidazole is kind of dangling from the top here, okay? And then we have 4 of these monomers kind of hanging out there, right? Okay, who cares? What's the point of this? Well, a couple of things to recognize. First, right, when you're looking at a new protein that you just discovered, right, if you see a heme unit, right, there's a couple important things to recognize from that. Second of all, the active site, well, notice the active site of hemoglobin is near the edge, right? And so what I mean by that is that if we're going to tab over here again, okay, let me zoom out. So can you see how close that heme unit is to the edge of the protein there? And if you want to think about it, right, remember, for our protein to do something, the substrate has to come in, oxygen in this case, has to get bound, travel around your body, and then get, transferred to myoglobin. And we're not going to talk about myoglobin in this course, but myoglobin is basically just kind of a derivative of hemoglobin. And, you'll pardon me if somebody's spinning in their grave at the moment. I'm an inorganic chemist, right? Not a biochemist by any means. And so when I say this, I'm not diminishing the impact or the purpose of myoglobin. I'm just saying it basically functions the exact same way. Who cares, though, right? All right. So what I'm saying is hemoglobin there, right? The heme unit is sitting towards the edge of the protein. So if you want your oxygen to bind quickly and get released quickly, okay, it should make sense that you want your active sites to be towards the edge of the protein, rather than kind of buried in the middle of a bunch of mess. Right? Because there is a kinetic aspect to this, right? If your oxygen, you have to travel all the way to the middle of some giant protein complex, it's going to take time to do that, right? As opposed to out on the edges, where you can very quickly come in, bind, and then get released when you need to, okay? So when you're looking at a protein structure, take a look at where the active site is. All right. Okay, let's move on to some other kind of important bits of information for us, right? If we're taking our generic depiction of the iron, right, sitting in our protein, okay. Iron is existing in the +2 oxidation state. That's important to recognize, but not that unexpected. Porphyrin, okay, your porphyrin, your heme unit, right, is a 2- ligand, okay? Now, it's important for us to start to look at the charges of the ligands that are coming into or are bound to the metal itself. Because if suddenly I say I've got a bunch of neutral ligands and I'm stabilizing a +4 oxidation state metal, okay, where are your counter ions, right? So remember, everything has to have a balance. Now, within biological systems, obviously there's sodium and waters and all this other kind of stuff that's usually around, but always pay attention to the charges of your ligands and your metals, okay? Now, iron is going to exist as +2, and that shouldn't be that unexpected. That's usually how iron exists in biological systems. Now, there are going to be exceptions to this, okay? And we'll talk about that when we get to it, especially when we get to the P450 enzymes, right? But it's not a bad assumption to make that iron begins in its +2 oxidation state. Iron in its +3 oxidation state tends to cause some problems, especially in aqueous solutions, right? It tends to be very insoluble. And we mentioned that briefly when we talked about the iron storage, ferritin, right? And how we have to how that has a bunch of iron 3s kind of hanging out in there. But the other important thing that we're going to need to know is that the iron 2 exists in the low spin state. Okay, excuse me. Sorry, high spin. Okay, so iron 2 in the high spin state. Now that's not too unsurprising either. Okay. Now we're going to have to start to make some assumptions. All right, so what does high spin and low spin mean and all that kind of stuff? Well, here's where we have to go back to our MO diagrams. Okay, let's assume we have an octahedral iron center. All right, that means we got our T2G set, right, and our EG set. It's our XZ, YZ, XY, right, Z squared, and X squared minus Y squared. Okay. So if we're a high spin iron 2, right, that means we are a 3d6, right? That is our electron configuration. So we'd go 1, 2, 3, 4, 5, 6, right? Okay, so what? Who cares? All right. Well, here's where we start to get into some of the debate about hemoglobin. And the debate comes into what happens, right? What happens once we bind iron, excuse me, once we bind oxygen to the iron center. And I should be better about this, right? There is that histidine that's kind of sitting on that end right there, okay? And so what happens as we start to bind iron to this position right here? Now we notice that's an open coordination site, and that's going to be extremely important. Because again, this goes back to the idea of kinetics, okay? If we're trying to bind iron very quickly and efficiently, right, we want oxygen to come in, bind to an open site, and then leave, okay? And so we have to have an open coordination site on our metal center. And so if you're looking at you're looking at an enzyme, right? If you see an open coordination site, that probably means something's going to come in and bind to it. And we'll talk a little bit more about this as we get a little bit further into it, right? But there is that open site on the top of the iron. And the histidine, right? The other histidine that's sitting up here is going to help us out with some of that stuff. I'm going to talk about what the role of that is, okay? So the question is, what happens when iron comes in? Okay, and the other question is, how does iron bind to the metal center? And you're like, well, what do you mean, how does it bind? Well, there's a couple of different methods, okay? Let's imagine we have an iron center, okay? Oxygen could bind kind of from an end-on manner like this. It could bind in a linear fashion like this, okay? Or it could bind in an end-on fashion, or a bent fashion like this. And all of these were proposed structures at one point in time. Okay, how does that work? How does that happen? How do we know? How can we assess? Well, blah, 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 blah. Well, here's where we're going to have to use MO theory again, okay? And so, let's see, how far along are we in this video? Oh, about 20 minutes. Okay, so this seems like a good stopping point. So, let's do a quick recap, right? And then in the next video, we'll start to introduce some of the different ways we can really dig down into how hemoglobin works. So, a couple important things to recognize about hemoglobin, right? We see our porphyrin ring. That means we're in an iron's in there, so we have a heme center. Our porphyrin ring is a planar molecule, right? The iron is sitting slightly above the plane of the porphyrin ring, right? The iron also has, right, an imidazole that is above it, blocking the open coordination site. And we've also got an imidazole bound to the other end, which is going to be important, okay? We know that iron is in its 2+ oxidation state. It's high spin, so it has 3d6. And there is the electron configuration for that. And then in the next video, we're going to talk a little bit about how and why oxygen binds to the iron center. Okay, I'll see you guys in the next video.